Hi everyone, let's talk about magnetic mass analyzers. Okay, so in this discussion, we're going to be talking about a mass analyzer, something that selects for different masses that uses magnetic fields. Now, how this is set up is we have an analyte aerosol coming through, so you have these very small particulates of analyte being sprayed into this chamber. They're going to basically move down this chamber. They're going to enter this magnetic field and they're going to curve, and if their mass is just right, they'll hit the detector. So we're going to talk about the physics behind it, but I just want to make one more distinction. The magnetic field, it starts at this purple region, and it's going to be pointing out of the page. It's going to be pointing towards us, right? The vector field points that way. So I just want to make that distinction before we specifically talk about this, but we'll just draw in the little field arrows here saying, okay, it's pointing out of the page. Okay, so let's review some physics here. You might have learned that the force felt by some particle in a magnetic field is described by the cross product of the velocity velocity cross the magnetic field times q. Now, this is simplified when we look at this final equation that you'll see in most algebra-based physics, where we have the magnitude of the charge, we have the velocity of the particle, and then we have the magnetic field. So what increases the force? Well, an increasing magnetic field, an increasing velocity. And it's a simple cross product, and if you remember the right-hand rule, hold out your right hand, designate and hold it out in a mutually orthogonal way such that everything is perpendicular between your thumb, your pointer finger, and your middle finger. Your middle finger is the force, your pointer finger is the magnetic field, and your velocity is your thumb. So hopefully you can see that with your right hand. I'll put up probably maybe a little visual. I mean, I have one here, but maybe I'll give some supplementary one with the hand shown. But middle finger, thumb, pointer finger. Okay. So the magnetic field strength is something that we can tweak, but something that's given by the molecules is its velocity. Now we have to talk about kinetic energy, and when these molecules are coming out of this aerosol spraying chamber, right? It's going to be spraying these molecules. They're all going to have a constant kinetic energy. And how this works is you make it such that the kinetic energy is roughly equal. Maybe there's a little bit of deviation. And if the better you can make this constant, the less band broadening you get in your mass spec. So keep that in mind. It is determined by mass and velocity, and if kinetic energy is constant, well, these are the two things fluctuating. Now, in a heavy molecule, the mass term is really large, so the velocity term is very small. But in the case that we have a very small mass, we have a very large velocity. So understand that distinction when we're talking about the velocity factor of this this cross product here. So let's talk about just an average particle as it's moving through in its trajectory. Hopefully you talked about this in your algebra-based physics before. You have a particle that's going to enter this field, and let's say at this point it starts to really feel something. Well, let's think about all the forces acting on it. Well, we know its velocity vector points this way, so let's think of that. And we know that the magnetic field is pointing out of the page, and let's just do a simple right hand rule. Point our thumb in the direction of the velocity, and the magnetic field points out of the page, thus the force is pointing this way. And we're going to notice some centripetal motion such that when particles move through this field, they begin to curve. And you want to make this area pretty narrow. I've exaggerated it, but you want to make it such that the only molecules that can go through are going to hit the detector and not and you can tweak the conditions to make it select for only one. Now, in this case, we're going to assume that the in-between mass, right, the not so fat, not so small, is going to make it to the detector. But let's talk about when a particle is too small or too fat. Now, if the molecule is too small, well, remember, it has less mass, so it has an incredible amount of velocity. And what does that mean? Well, that means that the force vector is really, really, really high. But the velocity is so fast that it's not going to really feel this force really pushing on it. So what happens is, as the red particle moves through, it's moving so fast, it just slams into the side, right? And we're going to designate this as an X. It's going to slam into the side of this detector. Basically, what's happening is it's moving too fast, and it doesn't get that curvature to it, right? It wants to do this, but it can't because its velocity is too fast. Okay, now let's describe a fat molecule. It has very low velocity because its mass is really high. All right, so keep that in mind. So let's consider its path. It's gonna go with a straight velocity until it hits the magnetic field. It's gonna begin to feel that force, but it's going so slow that it's just gonna smack right into the inner side, you could say, of the magnetic region. So it's just not quite right. But let's have an in-between molecule. So it has some amount of mass, it has some amount of velocity, and let's say this is the perfect velocity such that the force and its radius of curvature completely matches. So we're going to draw a little radius here. It's going to basically, its trajectory is going to follow around this radius of curvature. And in fact, that's what it does. When you have just the right mass, it gets curved and hits the detector. So what you do is you're going to start at a very low magnetic field, and you're going to raise the magnetic field. And what's going to happen is you're going to start selecting for these different masses. Only some masses are going to reach the detector. And what you're going to get as just raw data, I guess you could say, well, let's think about this. At some magnetic field strength, you're going to get some signal. Okay, and let's say you have the three analytes. So let's say at a very weak magnetic field, you'll probably only select for the fat ones. So the very low magnetic fields, you're going to get a peak like that. Okay, but at some magnetic field in between the small and the fat critical magnetic field, you're going to get your peak that we just saw. Okay, and then you're going to have to really raise the magnetic field such that the red particles can go through, or the small particles, and then you finally get that red peak. And that's what this mass spec is doing. It's different than a quadrupole. If you watch my last video, it's selecting because of increasing magnetic field. Now, I'm not sure the price of these, but they're pretty comparable in their quality. I'm not sure about the price, but I'd say this is a lot cooler, in my opinion, than the quadrupole, because it's really, really simple what it's actually doing, but it's selecting for all these crazy things. Now, notice that the computer isn't going to give this B; it's going to give M over Z. Okay, it will convert that using some math to find that. But overall, it's a very simple detector, and that's all we looked at. We just looked at the basic physics of a particle moving with some velocity through a magnetic field. We described the mutual orthogonality and how it moves in a curved path. Then we also described the kinetic energy equation, saying, okay, if you have some mass and some velocity at some constant ke, those things change, right? And then we described trajectory of some particles at some magnetic field strength, and then we described how you can change the magnetic field strength to get your different particles to reach the detector. So hopefully you found this helpful. If you did, please drop a like, comment, and subscribe. I greatly appreciate it. Hope that you have a wonderful day. Bye-bye.